we now are at a stage where we can say that we know what equation to solve for a general 3-dimensional turbulent chemically reacting non-isothermal flow. So using the time averaged approach, we can solve for a fairly complicated flow problem, but we still are saddled with the difficulty that our flow domain has to be very simple, because we have so far considered only rectangular dimensions, and it is fairly straightforward to extend this to say polar coordinates, where we have a flow through a pipe or flow in the annular space between two pipes, two circular pipes, or even for the case of flow over a perfectly spherical ball. So in all these cases one can use the appropriate Cartesian coordinate system or a polar coordinate system or a spherical coordinate system to represent the flow domain, and as long as we do that, we are quite okay with whatever techniques that we have learned. But if you are looking at a more complicated case, for example, if you are looking at a cricket ball where you have a specific stitch pattern that you would like to take care of, then you have a difficulty in describing the stitch pattern in a spherical coordinate system. If you are looking at a conical surface, if you are looking at a flow through a converging diverging duct, then you cannot represent the whole flow domain in exactly a polar coordinate system. We are looking at a flow domain which can be described in terms of constant, in which the boundaries of the flow domain lie along constant values of the coordinates. For example, constant x, constant y, constant z, constant r, constant theta, constant phi. So these are all the kind of orthogonal coordinate frames of constant coordinate directions, which can be easily represented using the techniques of CFD that we have learnt. But if you have, for example, a simple case of a flow domain which is not really like this, which we have already considered, but a duct like this. Here, this particular wall, if you were to describe this in terms of x and y coordinate system, this wall is along constant y line and this wall is along constant x line, and this surface is along constant z, and so on. But if you consider, if you want to describe the same thing in terms of x, y, z coordinate thing, one which is like this, then obviously this wall is not along constant y line. So it is, this does not fall into the general kind of technique that we have dealt with, and you can break it up into something like this, constant x, constant y, like that, but that is not a true representation of the surface. You have a surface which is coming up like that, and if you are very conscious of the nature of the surface, then you obviously cannot have this staircase kind of pattern to represent an inclined wall. For example, if you are looking at the effect of the seam on the seam on the cricket ball and the effect of that on the aerodynamics of the thing, then obviously you cannot treat that seam to be in the staircase pattern. You would like it to be a smooth surface. And if you consider another case where you have a rectangular duct with two tubes which are placed, and then you have flow going over these tubes, and so in such a case you cannot represent this wall here using a Cartesian coordinate system. Again, you would have to use something like a staircase kind of approach for this. Okay, so this, in these kind of cases where it is difficult to represent the bounding surfaces on constant x, constant y, constant z, or constant r theta planes like that, then we have a difficulty in using the conventional CFD that we have so far considered. We have to go from here, we have to tackle these kind of geometries in a different way. We have to treat them in such a way that either we have a system whereby we can treat the bounding surfaces as constant coordinate lines, not necessarily XYZ. That is one approach, and the other approach is to treat them using finite volume or finite element kind of methods. So when we talk about a geometry like this, we have the possibility of using coordinate transformation from x, y, z, which is what we are using here, to psi, psi, tau, something like this, where this is our regular coordinate system and this is a different coordinate system, and constant lines of psi, psi and zeta here will represent the values here, the bounding domains here. For example, we know that we cannot represent this as a constant x or constant y line in this, but if you had these coordinate lines such that this is psi and this is okay, let me put it psi, eta, psi like this. So if this is let's work in 2 dimensions. So this is our psi here and this is our eta, so that this corresponds to eta equal to eta 1, and this line, this surface corresponds to eta equal to eta 2, and this coordinate line corresponds to psi equal to psi 1, and this corresponds to psi equal to psi 2. Then these surfaces, the bounding surfaces, can be described in as being a coordinate constant plane like that. Okay, so in this case we can then do the discretization. So we have a grid line here which are parallel to the coordinate lines. In this case we can have grid lines which are parallel to these coordinate lines. And these are not along this direction, both y and x are changing. So in that sense this is not either constant x or constant psi line, constant y line, but this is a constant psi line and this is a constant eta line. So by doing a coordinate transformation from the xyz into a different coordinate frame in which the bounding surfaces are along constant values of these coordinate directions, we can tackle a complex geometry. And the simplest example of this is going from xyz to r theta z. For example, when you want to look at flow through a pipe, you don't represent the corresponding situation in xyz. You would use an r theta z coordinate system, and so you are going from x to r and y to theta. So you have changed, you have done a coordinate transformation, and in the process what we also know is that the governing equations also are changed. So in this approach, although we can describe the domain, although we are conceiving the domain in xyz coordinate system, the typical Cartesian coordinate system, we actually do not write down the equations in a Cartesian coordinate system because it's easier to write them down in a cylindrical polar coordinate system. So we go away from xyz coordinate system to r theta z coordinate system, and we deal with the transformed equations representing the same conservation. For example, del square T equal to 0 is a heat conduction problem. It represents a heat conduction, and this is applicable in any geometry. When we are dealing with a rectangular geometry, we write it as dou square T by dou x square plus dou square T by dou y square equal to 0 in xy coordinates. But if the same thing were in polar coordinates, in a circular pipe, we would be writing the radial coordinate equation for this, depending on whether it is r theta, r z, theta z. There can be many different two-dimensional combinations of that. So one approach is to move away from the restriction of xyz or r theta z or r theta phi type of transform coordinate frames that we are very familiar with, into an arbitrarily defined coordinate system psi eta zeta, such that the domains of the bounding surfaces on which we want to apply the boundary conditions will lie along parts of constant psi, eta and zeta lines. And in this way we can take proper account of the shape of the flow domain and its restricting boundaries, and therefore we can take proper account of the boundary conditions. And so this is one approach. The other approach is to use, for example, the finite volume method, which can be considered as a variation of the finite element method, wherein you do not deal with a structured grid, but we try to write down the conservation equations in each of these in a specific form, and thereby derive equations for the variables and how they change from point to point and all that. So the finite volume method is much more flexible. It does not enforce on you that you must have a structured grid, for example, with 4 faces in a two-dimensional coordinate system. The moment you say it's constant eta lines and constant sky lines here, every control volume has 4 faces, and that's a structured grid in 2 dimensions. In a finite volume method, you don't need to have only 4 faces, you can have more number of faces. So if you have a domain like this, you can make up a control volume, you can make up your you can have a control volume in which you start your equations either having 4-sided thing or a 3-sided thing and any sided. You can even make up this whole thing to be one control volume, and thereby you can tackle any complicated geometry very readily using the finite volume method. So there are 2 different ways of doing this, 2 different approaches. Both are practiced and both have their advantages and disadvantages. What we will do is we will try to take a look at the principles of each of these and try to understand what is involved in doing this. Once we understand this approach and this approach, then we can choose one of these 2 approaches and tackle any complicated geometry. And one would say that being able to deal with the coordinate transformation and being able to deal with non-orthogonal coordinate system satisfactorily has led to for example, the explosion of the use of CFD for a range of practical problems. So this can be considered as this has happened in early 80s in a way, and that is when people have started using this even in process industries in real earnest, because one is not restricted to tackling these simple geometries. One could consider the full complexity of the flow domain and then the corresponding flow changes, modifications associated with that. And finite volume method has also led to a similar kind of explosion, and it has led to lot more ease of computation and some of the lot more user friendliness into the use of computer codes has been brought in by finite volume and finite element methods, and this has also led to a great development in the usage of CFD, and nowadays both are practiced to such an extent that one can say that any complicated flow in any complicated geometry can be attacked using CFD techniques. Of course, there are lots and lots of areas and problems where CFD cannot be readily applied and used, but the range where one can say with confidence, yes, this is a problem that I can attempt and I can do resolve using CFD, that range of problems has tremendously increased with these two methods, which will enable us to tackle realistic geometries that are often found in practice. So let us try to understand first this and then this approach to tackling a non-standard geometry which will not fit into either of the Cartesian or cylindrical or spherical coordinate system. So what we are looking at is that the approach that is followed in this is that, as given in this example, we abandon our attempt to describe the flow domain in XYZ coordinate system and we move on to a more convenient coordinate system in which the bounding surfaces are along constant coordinate lines. And along with the process, when the moment we abandon XYZ and use this, we have to represent the variation of a parameter of interest not in X and Y but in terms of dou t by dou r. For example, if it is r theta, dou square t by dou theta square and dou t by dou z, all that. So in that sense we move away from X and Y and we have to write in terms of r and theta. So we have to transform our coordinate system from here to here. So this is where the idea of two grid approach comes into picture. It is not a multi-grid. We are looking at a physical plane and a computational plane. Physical plane is the plane in which we describe our system. For example, this is our domain and this cylinder is placed here and this cylinder is placed here with the center of this and this radius is this and so on. So this is the XYZ plane. But we do not solve the equations in this plane. We transform from this physical plane into psi eta zeta here, and then we transform our equations also from here into this. We compute the solution so in the computational plane here and then transform the solution back into the physical plane. So we have an identification of where we want to have the variables of interest here, and we export them into the computational plane, which is described in terms of psi eta zeta, and we write the governing equations in this plane. We discretize these so we are talking about delta psi, delta eta and delta zeta being used to express these things. So from these we convert the governing equations into a phi equal to b, where A consists of these, instead of delta x, delta y, delta z, we have now delta xi, delta eta and all these things. And then we finally get, by solving this, we get phi at every xi, eta, zeta that we wanted to do. Now we have an understanding of which point of xyz corresponds to which point of psi, eta, zeta. So once we have this phi at many points on the computational domain, we say that since this point there is a one-to-one mapping between the computational plane and the physical plane, then we say that this point, which is computational plane of psi naught and eta naught and zeta naught here, has a corresponding physical space location, which then we say that xyz. So there is a one-to-one mapping between a point in the physical plane and a point in the computational plane. We do all the computations, that is starting with the governing equations, discretization, analysis, and converting into a phi equal to b, solution of the simultaneous equations, and all that is done, and finally we get the solution of phi in the computational plane. And since we know what point this corresponds to in the physical plane, we say that at this point in the computational plane the phi is this, and therefore at the corresponding point the value of phi is here. So only the solution is given back, is mapped from the computational plane into physical plane. So in the process we have a mapping of the physical plane, the geometry in the physical plane into the computational plane, and using that mapping we transform the governing equations which are described in physical space in terms of xyz into computational plane, and the transformed governing equations are discretized and solved in the computational plane to get the solution in the computational plane. And using that mapping between the physical space and the computational space, we map the solution back from computational plane into physical plane. So we have somebody else doing all the computations and giving us the solution, and that somebody else does not obviously work in xyz, he works in a coordinate frame of his own interest. So associated with this approach is the idea of deriving a mapping between xyz, between the physical plane and the computational plane, and transforming the computational plane, the governing equations into equations which are applicable in the computational plane. Once that is done, it becomes the same old mathematical problem. We have certain derivatives which we try to approximate using Taylor series expansion and so on. We put them together, we do analysis for consistency and stability, and then we choose a discretization scheme which is good, and then that becomes a matrix equation. We have several such matrix equations and we solve them using either Gauss-Seidel or multigrid, or whichever which we think is the important thing, is the most appropriate, and then we get the solution here. So in this approach what we need to understand in addition is to this transformation of physical and computational plane and transformation of the boundary conditions, and we will see what is involved in this process. First we will look at the transformation from xyz into psi, eta, zeta here, and we notice that because of this x is a function of psi, eta, zeta, and y is also a function of this, z is also a function of this, and similarly psi is a function of xyz, eta is a function of xyz, and zeta is also a function of xyz in the general case. So we can write x is a function of these things, so we can write dx equal to this is a function of dou x by dou times d eta, and similarly we can write dy, which is a function of those three variables, can be written as the specific derivatives here depend on what kind of transformation we have. And we can we can introduce a small simplification of notation here. This dou x by dou psi here we write as x subscript psi. This indicates a differentiation of this with respect to psi here. So we can write this x sub eta just a change of notation, otherwise it's nothing. Plus y eta d eta y psi y zeta d zeta, and similarly I can write dz to be by the same token z psi d psi plus z eta d eta plus z zeta d zeta, and so we can write, therefore we can also write from here d psi, which is function of xyz, can be written similarly as psi x dx plus psi y dy plus psi z dz. D eta can be written as eta x dx, eta y dy plus eta z dz, and finally d zeta can be written as zeta x dx. This obviously means dou psi by dou x as per our notation, and psi y dy plus psi z dz, which we can write in matrix notation as psi x, psi y, psi z, and eta x, eta y, eta z, zeta x, zeta y, zeta z. So we can combine all these things here and say that this is equal to d psi, d eta, and d zeta. What it means is that the total differential of psi is now a sum of differentials with respect to different coordinates that of which this is a function here, and this transformation, the differentials, the total differentials dx, dy, dz can also be expressed like this. We can also write equal to, here we come x psi, x eta, x zeta, y psi, y eta, y zeta, z psi, z eta, z psi times d psi, d eta and d zeta. So we can substitute this for dx dy dz here in this, and therefore write d psi d eta d zeta equal to psi x, psi y, psi z, eta x, eta y, eta z, zeta x, zeta y, zeta z times, we substitute for this thing here, x psi, x eta, x zeta, y psi, y eta, y zeta, z psi, z eta, z zeta times d psi, d eta, d zeta. So from this we have this here and this here. So obviously these two should give us the identity matrix, the multiplication of these two is identity matrix, and therefore we can write a very useful result, psi x, psi y, psi z, eta z, zeta x, zeta y, zeta z equal to inverse of psi x, x psi, x eta, x zeta y zeta, z psi, z eta, z zeta inverse, and this can be written as J, which means the Jacobian. We can y eta z psi minus z zeta. So these two minus these two. So that is that's the first term, and then here we have minus y psi, z zeta minus y zeta, z psi, and y psi, z eta minus y eta, z psi. So these are the three elements here, and here we have three more, x eta, z psi, x zeta, z eta, x psi, z zeta minus x zeta, z psi minus x psi, z zeta minus x eta, z psi, and x eta, y zeta minus x zeta, y eta minus x psi, y zeta minus x zeta y psi, and finally x eta x psi y eta minus x eta y psi. So the matrix of the transformation, so that is dou psi by dou x, dou psi dou x, dou psi by dou y, dou eta by dou y, all these things are given in this, where J is known as the Jacobian of the transformation. This is the determinant of zeta x, zeta y, zeta z, eta x, eta y, eta z, and zeta x, zeta y, zeta z. And this can also be written as 1 by J inverse, inverse of the transformation. So this is 1 by dou xyz by dou psi eta zeta. So this is 1 by x psi x eta x zeta, y psi y eta y zeta, z psi z eta z zeta, and finally this is equal to 1 by minus x eta y psi z zeta minus y zeta z xi z x zeta times y psi z eta minus y eta So this is what J is, and what this actually tells us is that this matrix, each of this psi x is given by J times this here, and similarly this is given by J times this, and this given by J times this, and so on, and together these relations define the how we can evaluate the matrix of the transformation. These metrics are important because these metrics appear in when we transform our governing equations from xyz to psi eta zeta like this. So we need to be able to evaluate this, and these relations and the corresponding relation for x and all these things tell us that if, for example, in doing this, if we know the relation of how x, y, z are related to this, if we know this, then we can immediately differentiate this with respect to psi, eta and zeta and evaluate the x these metrics, and from this we can get the Jacobian, and these are already derivable from the known transformation here. So we can therefore get the corresponding matrix of psi x and psi y and psi z like this. So either we should know this or we should know this. If we know this, then we can get x, xi and all these things, all these things from a similar relation, or if we know this, then we can get the corresponding metrics in this. Now the why we want to do this is that when we are doing computations in the computational plane, we are going to write derivatives with respect to derivatives of the parameters of interest with respect to psi, eta and zeta. So we want to express things in terms of dou phi by dou eta, dou psi, like that, and so that is what is going to appear, and that is where this information comes. And here what we have is, this is the mapping that we are looking at in terms of x, in terms of psi and all these things. So how, for example, if we can express this in terms of x and y, then we get a transformation like this, and if we express the corresponding this line in terms of these two things, then we get a transformation like this. So when we start about doing the problem like this, we want to have a coordinate system in which these lines here correspond to constant x and constant psi lines. So from finding this transformation, one way of finding the transformation is to come up with some analytical thing. For example, we can say that this line, if this is theta here, then we can say that this is equal to this divided by tan theta, or something like cosine theta is what this will give us. So we can have this kind of algebraic or trigonometric expressions between the x and the corresponding xyz and the corresponding psi, eta, zeta lines. Otherwise, in the general case, we have to come up with a numerical description of this kind of transformation. So that is where these transformation relations will actually be helpful. These will be using this, one can come up with a coordinate frame, coordinate transformation numerically for an arbitrary coordinate, for an arbitrarily complicated geometry like this. So a geometry which is described in this physical plane like this can be transformed into a corresponding computational plane description, in which we have, for example, psi here and eta here, and lines in this computational plane we have grid lines which are straight and easy and described in terms of constant delta psi and constant delta eta, like this. But this line here, in reality, that is in the xy plane, may correspond to something like this, and this line may correspond to something like this, and thereby, okay, let's put one more here, and this line here corresponds to this, and this line corresponds to this, and this corresponds to this. So you have this line here corresponding to this, and these lines may correspond to something like this, so what is a rectangle here with delta psi and delta eta as the 2 dimensions, in physical plane it's actually like this. This represents that particular volume. So this transformation from a physical plane, so the shape in computational plane is nice and easy, but the same thing is made to correspond to the real complicated shape in the physical domain. So as a result of this, we may get something like the velocity or something at this point, and that point corresponds to, in the physical plane, to some here. So we can get this value by doing the computations in this and getting the value here, and then saying that this control volume corresponds to this, so this centroid corresponds to this, and this is where I have the points. So there is a certain relation between what these coordinate lines are in computational plane and what the coordinate lines are in the physical plane. So in the physical plane, the psi eta zeta lines are curved and they are allowed to curve in such a way they go through they also go through, at least some of them will go through the bounding surfaces here. But in the computation plane, for ease of discretization, these are lines of constant psi and constant eta, so that you have just a square matrix or a rectangular matrix with rectangular domain with delta xi and delta eta. So this is the kind of relation that we are looking at. This is the advantage also that we are getting by doing this transformation. A complicated shape here with curved boundaries is made to represent in the computation plane a rectangular boundary, and the treatment of these rectangular boundaries is very easy in a computational domain, but the treatment in the physical domain is more complicated. So instead of doing all the derivatives and all these things in the physical plane along curved boundaries, we do it in the computational plane along simple grid kind of approach, and then we come back into the physical plane. And in the process, if we say that this represents this, the corresponding variation of dou t by dou x here corresponds to something else in terms of dou t by dou xi and dou t by dou eta, because now x is a function of both psi and eta here. So dou t by dou x now becomes a function of dou t by dou eta and also dou t by dou xi. So one can say that this is equal to dou t by dou xi times dou xi by dou x plus dou t by dou eta times dou eta by dou x. And one can see that this is our psi x and this is our eta x. So these are the metrics of the transformation that we are expressing here. So, and that is how we make the relation between, we do the whole computation for this complicated shape. We get a relation, we get a transformation between xyz space and psi eta zeta space, and using this kind of chain rule of differentiation, we convert dou t by dou x, dou t by dou y, dou square t by dou x square, all those derivatives into derivatives in terms of psi eta zeta, and in the process we have to make use of we have to come up with these metrics of the geometric transformation, and these we compute from the corresponding variation of y with respect to eta and z with respect to zeta, like this, and then using this transformation rules we get the metrics of the transformation, and that will give us the overall discretized equation in terms of the derivatives of the variable with respect to psi eta zeta and the metrics. So the metrics are known from the physical grid generation, so that you have now a discretized equation having only the derivatives as the unknown variables. So those derivatives are approximated with difference approximations, and then the resulting partial differential equation is converted into a phi equal to b, and then you solve finally for phi of psi eta zeta here, and then from this centroid you go back to here and say that this is the value of phi in the physical plane. So this is the approach that we solve, that we use here. We have done only part of this. We have seen how we can get the metrics of this kind of transformation from a knowledge of the variation of x with respect to this physical mapping. We will also look at how to do the transformation and what this transformation entails in terms of CFD solution. We will see that in the process of this transformation additional complexities arise. We look at these additional complexities and then take a complete view of this approach for dealing with complicated geometries. That is the approach where we have to do a coordinate transformation and then carry out the solution.